Hello class, welcome to lesson 8 of the calculus series. So introduction to the derivative. We in the first 7 lessons, we introduced the ideas of sort of what you would do at the end of pre-calculus, or beginning of calculus 1, which is the idea of a limit and various types of limits. So now we're going to use the idea of the limit in order to introduce the derivative. Okay, so this is sort of like the beginning of differential calculus. So in the first lesson, you might recall that we looked at the tangent line problems. There was essentially a couple of problems in calculus that we wanted to address and throughout the course. And the first problem was the tangent line problem. And if you remember, there was a tangent line problem and then there was the area problem. The tangent line problem is addressed in differential calculus, which we're going to introduce in this first lesson. In the area problem, we'll tackle that when we look at integral calculus. But for the tangent line problem, the idea was that in pre-calculus or algebra, you can find the velocity of a car at a specific time if it is traveling at a constant velocity. So in this case, in order to find the velocity of this car moving, with this curve, you simply needed to find the slope of that curve, and that gave you the velocity, right? So the velocity was the change in the distance over the change in time. So that was the slope. And in calculus, since the velocity varies depending on the time, so for example, the velocity could vary here, it could vary here, and so the idea is that in order to find the instantaneous or in order to find the velocity at a specific time, you have to actually draw these tangent lines, right? So if I wanted to do the velocity at time t1, I needed to get the slope of this tangent line. And the tangent line is the line that just touches the curve at that one point. Okay, so if I wanted to get the velocity at that specific instant, in other words, the velocity given if you're driving the vehicle, this is the velocity given by the odometer, right? Which gives you that speed, right? That's the slope of the tangent line that it's giving you. So if I do the rise over run for this tangent line, that gives me my velocity, okay? And this is essentially what we're talking about when we're talking about the derivative, right? We're introducing the derivative in terms of this slope of this tangent line. And if I were to do the slope, that would be my instantaneous velocity at that instant. If I want to do the velocity at t2, it's going to be different, right? Because the slope of that tangent line is naturally going to be different if the graph is a curve that changes over time. And so in order to do this, we need to use the tools of calculus, okay? So what we're going to do is we're going to try to figure out what the slope of the tangent line is first by finding the slope of the secant line, okay? So let's say we have this curve and we wanted to find the slope of the tangent line at x1, okay? Well, in order to do that, I need to first draw what is called a secant line, right? So if I wanted to find the tangent line through here, well, first I need to pick a point just outside of x1, such as x2, and we'll go ahead and say that this y value is now y1, and this y value is y2, right? So we need to figure out the slope of this line. So let's draw that line there. So that's my secant line, okay? So that's called the secant line. A secant line is a line between 2 points on a curve, right? So here we go. There's our secant line. And we need to figure out what the slope of that secant line is. Well, the slope of that line is change in y over change in x, right? So in other words, you subtract the 2 y values, subtract the 2 x values, and then you get your slope. In other words, rise over run, right? So the rise here over the run there. Okay, so that's great. So we got our secant line. Now let's assume that this is x1, which is x, and let's call x2 x plus delta x, where delta x is the space between x and x plus delta x, right? So delta x could be like, for example, if x was 5 and x2 is 7, then delta x would be 2, right? Because delta x is the change between those two values. So 5 plus 2 is going to give me 7. So that's just an example, okay? So let's just generalize it and say x plus delta x. So there's a space delta x in between them. And then what we want to do is we want to find the slope of the secant line in terms of this x plus delta x. Okay, so remember that this here is y2, or y1, sorry, y1, and this here is y2. So, and we can also refer to y as f of x, right? Because we know that the function here is y equals to f of x. So we can rewrite y2 as f of x2. But remember that this is now x2, right? So we can write it as f of x plus delta x. We can rewrite y1 as f of x1, but x1 is just x, right? So we can write it as f of x. So if we do that and we do rise over run, well, y2 minus y1 gets replaced with these two, right? And then x2 we said was x plus delta x. x1 is x, okay? And so this is what we get if we plug it into this formula, right? All right, so in that case, we're just simplifying a little bit more, realize that the x's cancel there, and so you get this formula for the secant, the slope of the secant line, okay? And that formula is known as the difference quotient. So this is a very common quotient, right? They're called the difference quotient, has a name for it. And this gives you the average rate of change. Again, in other words, it gives you the slope of that secant line through any 2 points connecting, on that curve. So how can we use this to get the slope of the tangent line, you may ask? Well, what we're going to do is we're going to take this idea, right? And we're going to do a bunch of secant lines, and we're interested in trying to get this point right here to get closer and closer to this point right here. And as it gets closer and closer, you'll see that this point will merge with this other point. And in other words, that secant line is going to turn into my tangent line, okay? So let's take a look. So we moved x2 from here to now here. So notice that it's moved. So now this is going to be where my x plus delta x is now. And so now it's located here at this point. So then if I draw a secant line between these 2 points, I get this. So notice that this transforms to this, right? As this point gets closer and closer. This sounds a lot like a limit, right? Limit is when you try to approach a value, right? You try to approach it without ever actually reaching it. This is the idea, is we want this delta x. So right now from here to here it was delta x, but then we want that to get smaller and smaller. So we want it to go from there to here until it gets so small that the points merge. So let's continue doing this, shall we? So if we continue, now this time we're moving x plus delta x here, so we're going to have a point here. Notice that it's getting closer. And then I can draw my secant line. There's my third secant line. And you're starting to see that point is getting closer. And as in the limit, as that gets super close, we are going to get our tangent line, okay? So if we continue, so in other words, if I make delta x as small as possible, meaning the delta x approaches 0, then this separation starts to decrease, right? And as it does, you get from the secant line to the tangent line. And you can get the tangent line by taking this limit. So this is tying in the idea of limits with slope, okay? And as you do that, if I erase these other secant lines, I still got a secant line here. This is where it's super duper close to it. So my delta x is small, right? But we want that to approach 0 ideally, right? So then what happens if it gets like so close it's basically merged with it? We get our tangent line. So this is the concept of the tangent line and how it ties in with the idea of limits. So now we know what the formula is to find the slope of the tangent line, is to be able to calculate this limit. Okay, so great. we got the formula for this, and just recall that the slope of the secant is the average rate of change. This is the AROC, the average rate of change, because the average rate of change is called the average for a reason, because if I get these 2 points, this is not the exact velocity, it's just averaging over this curve, right? Whereas the slope of the tangent line, m tan, is the instantaneous. It's the speed that you would get on the odometer at a particular time. So at one instance, if it says you're driving 60 miles per hour at that particular point in time, that's your instantaneous velocity, right? That's the slope of your tangent line. Your car is traveling 60 miles per hour instantaneously at that time, right? And then of course it changes over time, which is the whole point of this idea. And so this is the slope at that instant. Okay. All right. So the idea here is that the slope of this tangent line is referred to as the derivative. Okay, it's referred to as the derivative. And this is the main idea that we want to address. Okay, so let's find the definition of the derivative. The definition of the derivative is the limit as delta x approaches 0 of the difference quotient. Remember that was the difference quotient, right? So we take the difference quotient and we take the limit of that difference quotient as the separation goes to 0, the delta x. Notice we have f prime of x. That's the symbol that we usually use for the derivative is f prime, but we'll go over some other derivatives, some other symbols of the derivative. I want you to also recall that the slope of the secant line, which is normally written as change in y over change in x, like this, right? Change in y over change in x. So the slope is normally change in y over change in x, which is the y2 minus y1 over x2 minus x1, that whole thing, right? Now, if we compare this is for the secant line, compare this to the derivative symbol, well, the derivative, if we look at this, we generally use delta y, delta x for the secant line, but for the derivative, we actually change it to dy dx. And so we say that the slope of the tangent line is not delta y, delta x, but dy dx, okay? So we can kind of distinguish between those two things. So we got the instantaneous, the dy dx, versus the average, delta y over delta x. There's some other symbols too. We have y prime, and sometimes we have this. This denotes that we are actually doing the derivative of f of x. So that's an actual derivative operator. But there's a bunch of symbols for the derivative, but those are the main ones. So another way of thinking of dy dx is you take the limit as delta x approaches 0 of the secant line, right? That's exactly what this is saying here. This is just a fancy way of saying delta y over delta x, in other words, with the limit. Okay, so in other words, that's just a fancy way of saying that. Okay, so we got the definition of the derivative. How do we apply it, right? So we want to find this, remember the derivative is the slope of the tangent line, which is the instantaneous rate of change, the instantaneous velocity, for example, at a particular point in time. So we want to find the slope of the tangent line at x equals 2 for the following function. So this is just a line, right? But we want to find the slope of that. Now, so let's go ahead and use the idea of the derivative. So this is the definition of the derivative, right? It's the limit of the difference quotient, change in y over change in x, but looks a little fancy. So we take that limit, but okay, so what is f of x? Well, we know f of x is 3x minus 2. And we know that f of x plus delta x is obtained when you replace x here with x plus delta x, right? So you replace the x with x plus delta x, and so this is what you get. This was originally x. So it's normally 3x minus 2. It's now 3 times x plus delta x minus 2. So, and then you take the difference of those two things. All right, we got to do a little bit of algebra here. Distribute the 3 there. And then just clean and distribute the negative here. All right, and then notice that the negative 2 and the 2 cancel. The 3x and the negative 3x also cancel. So we're left with 3 delta x over delta x. And then again, notice that the delta x cancels. leaving us with the limit as delta x approaches 0 of 3. But we know that the limit of that is just 3. All right, so the slope of the tangent line at x equals 2 for that line is 3. The slope is 3. And if you think about it, that makes sense because 3x minus 2 is just a line. This is just a line, which is drawn here. What's the slope of a line? The slope of the line is constant. The slope of the line is the same everywhere. So if I were to pick 2 points on here, say from, well, and it's kind of hard to tell from here, but let's say we picked from here, this is negative 0.2. Yeah, and then from there to say, let's say a little bit above that. So, so we're saying that, well, we don't have enough space on here, but here the slope of this line is, you know, change in y over change in x, which is equal to 3. But that's also equal to the derivative, right? The derivative is also 3. And that, if you think about it, that makes sense because the derivative is the same as the average rate of change because the slope is the same everywhere. This is equivalent to, you know, you're driving with a constant acceleration, right? So, or in this case, you're driving with a constant velocity. I'm sorry, you're driving with a constant velocity, and so you're either, and if you think about it, you're just holding the pedal just enough for your speed to be the same. Your speed is the same. So if you're on a highway and you put it on cruise control, 60 miles per hour, for example, your curve is going to look like this for this if this is distance over time, right? And so this is saying that you're covering the same amount of distance per unit time. In other words, your velocity is the same. Okay, so that makes sense if you think about it that way. Now, if you look at example 2, this time we're going to do something a little bit more interesting. The other one was just a linear function. This one is a quadratic. So this one actually is more interesting of a result. So let's find the slope of this quadratic function at -1. X equals -1. Well, this is the definition of the derivative, if you recall. So if we use that definition, we'll go ahead and plug in x plus delta x into x here, so you can get x plus delta x squared. And then remember, this is your f of x right here. And then you're going to need to FOIL this, right? Because this is x plus delta x to the second power. So again, just to kind of show you, x plus delta x squared is equal to x plus delta x times x plus delta x. So you're going to need to expand this and FOIL it essentially. So you get x squared plus x delta x plus x delta x plus delta x squared. So this is how you get this, because this is going to be 2x delta x. So just to kind of show you the steps in between, and that's how you get that expansion. You're also going to need to distribute the negative here and here, so that's why we have 2 negatives there. Okay, so then if we kind of simplify here, x squared cancels out, we got the 3's cancel out there, and we're left with everything else with the delta x stuff. Then we're going to pull out the delta x from this expression, and if we do that, we can cancel out the delta x's. At least one of them anyways. Because the other one we're left with 2, there should be an x right here, that's a typo. So say 2x plus delta x, but then if we plug in delta x as 0, then this here goes to 0, right? So we're going to make that go to 0, and that leaves us with 2x. So the derivative of this function is 2x. So the derivative actually changes, right? If I plug in x as a number, that slope is going to change. So let's go ahead and plug in, let's get rid of this. Let's plug in 1 into the derivative, so it's going to be 2 times -1, which is -2. So here the slope of the tangent line varies based on the function. So if you were to graph it, if you were to graph this function, x squared plus 3, which looks kind of like this, then if you were to do the slope at -1, let's say like here, and you were to find the derivative of that, they're saying that the slope there, the slope of this line is -2. And if you were to do the derivative at x equals 3 or something like that, and let's say over here, then your tangent line would be like this, and then your slope would be some other value, right? So let's say that that's x equals 3. Then your slope would be 2 times 3, right, is 6. Okay, so your slope is changing over this curve. All right, so again, we're going to be doing some pretty heavy examples. We want to show you the limits of complicated functions, and then in a future lesson, we'll actually go over some shortcuts to taking the derivative. But for now, it's a little bit tedious because we have to do the limit process, which naturally, it's important to understand how to take the derivative using this limit. However, in future lessons, we'll be able to look at some shortcuts. But some of these examples are going to be pretty tedious, right? Let's look at this function already. It's already, speaking of the tedium, if we look at this function, if I were to apply the definition of a derivative there, well, we got a cube here, so we're going to need to expand that, right? So if I do this, I'm going to be putting x plus delta x into that, and then that's going to be to the third power. And then I got to plug in x plus delta x into here as well, so that's this guy right here, right? And then we subtract the original function, which is that. Okay, so we do that. We have to expand x plus delta x cubed. Now, which means that we have to, do x plus delta x times x plus delta x times x plus delta x. We gotta FOIL it, triple FOIL it, I guess you can call it. 3 of them. Expand it. You can also use the binomial theorem to expand it too, if you're comfortable with that. But in any case, when you expand this, you get this part right here. Okay, so take the time to kind of expand that. It takes a little time, to get used to that, but it's not so bad. It just takes time. You're going to distribute the -5 to this, so -5 times x, -5 times delta x. And then, of course, you're going to need to distribute the negatives here, here, and here. So double negative makes it positive, etc., etc. And so you get this really long line here for the fraction. And then you notice that a lot of these terms cancel, right? So a lot of these terms end up canceling. And it simplifies a little bit. So let's go ahead and, so it simplifies to that. That's with all the terms canceling. And then you can pull out a delta x. So each of these have a delta x in common that you can pull out. So you can pull out exactly one of them, and then these will cancel. So there you go, they cancel, and then we're going to go ahead and plug in the limit. We're going to plug in 0 in for delta x. So every time you see a delta x, you're going to plug in 0 into it, okay? So plugging that into the limit, this goes away, so leaves you with 3x squared minus 5. So there's my derivative. Hopefully you might be seeing a shortcut. You might be seeing a quick way of doing this. If not, that's okay. In another lesson, we'll look at some derivative rules. But for now, in this lesson, we're looking just at the limit definition. But there's our derivative. Okay, so now we're going to look at the alternative form of the derivative. There are a couple forms of the derivative. So remember that the form that we looked at is f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x, right? That was the first form that we looked at. So this is form number 1. This is form number 2. The good thing about this form is that you can plug in a value for x right away. So you can plug in c, okay? That's the good thing about this form, is that you can just plug in a number where c is a number, okay? And you can also do derivatives from the left and derivatives from the right using this definition. So that's also the advantage of using this method. The advantage of using method 1 is that it gives you a formula for the derivative for every single value of x, and then you can start plugging in values of x afterwards. So they all have their pros and cons. All right, so these are the forms. We're going to be using these in order to take derivatives from the left and from the right, things like that. Okay, so since I went over those 2 forms, we're going to use those 2 forms in some of these examples that follow, including this one. So we're going to find the slope of the tangent line at x equals 3. So first we're going to try to do the first definition, and then we'll look at the second definition. So let's look at the first definition. Let's do that first. So using the first definition, we have this, the difference quotient stuff. And then remember, we're replacing x with x plus delta x. So we have that here, 1 over x plus delta x minus the original function 1 over x. And now what we're going to do is we're going to need to combine these two fractions, all right? So again, if you want to see how to do that, we can just quickly show you that. So if I have these two fractions, I want to combine them, I need a common denominator. So my common denominator is going to be obtained by multiplying these two denominators. So if I multiply these two denominators, I get this, right? And I'm going to multiply this like this. So now the two denominators I multiplied, and now we have common denominators. But again, if I multiply this by x plus delta x, I have to do it here as well. If I multiply this by x, then I must do it here as well, so that I don't change the overall expression. But then if you do that, I get x minus delta x, which is what I got here, okay? So that's exactly what it is under a common denominator. So this is how I got that expression on the top. And then notice that the x cancels out here. X minus x goes away. And then we have to make sure to distribute the we're going to make sure to distribute the negative sign here. So this is going to be negative. That's why I have the negative right there. All right, and then we're going to bring this denominator down, which is what I do here. And then notice that these delta x's cancel. So that leaves me with -1 over x times x plus delta x. And guess what? I'm going to plug in 0 for the delta x now. So I'm going to plug in 0 for the limit. And when I do that, I get, well, this is 0, so I get x squared on the bottom. So -1 over x squared is my derivative. At this point, I can now start plugging in x equals 3 and get my tangent line slope at 3. So I'm going to plug in 3 into that derivative, and I get -1/9. So that is the slope of the tangent line at x equals 3, and that is what we're looking for. Okay, we're going to show you the alternative definition. So the alternative definition, if you recall, is f prime of c equals limit as x approaches c of f of x minus f of c over x minus c. So if you look at it, that models that perfectly. C is equal to 3. In this case, this is my value of c, and that's why we replace c with 3. Okay. All right, so there's my alternative form. And so if I wanted to solve that, again, I have 1 over x, that's the original function, and then I got plugging in 3 into 1 over x, that turns into 1 over 3, right? All right, I subtract those. And then I need to combine these two. Again, 1 over x minus 1 over 3. You need a common denominator, so I'm going to multiply this by 3, multiply this by x, and then show equal treatment. If I multiply on the bottom, I need to do the same on the top. So this becomes 3 minus x over 3x, which is how I got this, all right? Okay. And then I can bring this 3x down to the bottom. So really what I'm doing when I do that, this is what I'm doing. I'm taking this fraction, remember, to divide two quantities that are fractions. I need to basically, dividing by fractions is the same thing as multiplying by the reciprocal. So I need to keep this fraction, and then I need to flip this other fraction, and then convert this to a multiplication problem. So I'm going to flip this, and I get, this turns into this fraction times the 1 over x minus 3, so the reciprocal of the bottom fraction. And then I get this expression, which I can multiply straight across, which is how I get the 3x times x minus 3 right over here, okay? All right, and then I'm going to pull out the negative from the numerator there, and when I pull out the negative, if I distribute back, you'll notice that I get the original, okay? So pull out the negative. The reason why I want to do that is because this should actually be, by the way, this should actually be a -3, not a +3, so this is a typo. If I distribute this back in here, I should get the original there. So the reason why I do that is because the x minus 3's now cancel, okay? Leaving me with negative 1 over 3x. Then I can plug in the limit into there by doing a direct substitution, and I get negative 1/9. And lo and behold, we get the same exact answer. So, sorry, I've zoomed in on that for a little bit, for a short while. But you get the same exact answer for the alternative definition. Okay, so we're going to go ahead and now discuss horizontal and vertical tangent lines. All right, so sometimes you won't always get diagonal vertical lines. You'll sometimes get vertical tangent lines. You'll sometimes get horizontal tangent lines. And these are special. And you need to know, when you get which one, right? Or how to obtain them. So, and not every curve is going to have a horizontal and vertical tangent line, but some of them have one or both or neither. In the case of this function, this is a pretty interesting function. We'll do the derivative of that in a later example. But for now, here's the graph and how it looks like. Notice that if I were to look at this value here, and I were to do the tangent line, that would be completely flat there and here. The velocity at that point peaks out, and so you notice that as I draw a tangent line, it goes like this, then like this, and then it flattens out, okay? And then, of course, after that point, then it starts going down, 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 right? Or sorry, that's a wrong one. It goes like this. And then at this point, it starts going so down that it becomes vertical, right? At 2. So we have our red horizontal tangent lines that you can see there. And this is where the derivative is 0. So this is where the slope equals 0, which is the derivative, right? And if I look at the vertical tangent lines, like this is what I was trying to show you earlier, this is horizontal, and then it goes down like this, and then it goes down like this, and it goes so down, it's basically vertical. It's all vertical, okay? And those are called my vertical tangent lines. And notice that the slope of them is undefined, right? So the slope is undefined or infinite, right? So that's how you determine whether the vertical is if you look to see if you try to calculate this guy and it's undefined or it's infinite. Okay, so let's take a look at sharp turns. So we know that a horizontal tangent line has a slope of 0. A vertical tangent line has an infinite slope or an undefined slope. And now let's take a look at a sharp turn. So for this function, this is an interesting looking function, right? But if I were to take the derivative from the left side, remember this is the formula for the derivative from the left, right? Using the alternative definition of the derivative. And I notice I have a sharp corner here. So let's try doing the derivative from the left as x approaches 0 from the left side. What happens to the derivative? Well, then you start noticing that the derivative looks like sort of like this line, right, at 0. So as I start approaching the slope here, these slopes are not very good, by the way. But yeah, the slope there, slope here, and then eventually you get to this other slope, right, as I approach this from the left. But then if I do it from the right, then I get a slope that looks like that. And so we get this slope. This should touch at one point. So if I touch here, then the slope is going to look something like there. If I touch here, slope is going to look like that. And then it's eventually going to get to this red line as I approach from the right. But notice that those two slopes, the left and the right, are different because of that sharp turn. So because the limits don't agree, the values are actually different, the derivative actually doesn't exist. So if you have a sharp corner, the derivative is not going to exist there. Okay, so let's take a look. How do we find horizontal tangent lines? Let's look at an example. So this is actually the example we looked at earlier. So we've already calculated the derivative of this, and we found that the derivative was 3x squared minus 5. So I'm not going to go through that process again because we actually did it in a previous example. So there's our derivative. So then we're going to figure out what the horizontal lines are by setting it equal to 0, because we know that the slope of the tangent line, if we have a curve, if it's flat, the slope is going to be 0, right? In other words, the derivative is 0 at that point. So we're going to set the slope equal to 0 and then solve, and then that tells us where the tangent lines are flat, Okay, so let's solve that. So in order to solve this, you're going to add 5 to both sides, right? So you get 5 equals 3x squared, then divide by 3 on both sides. And so you get 5/3 equals x squared, and then you have to, of course, take the square root. But then you can not only take the plus square root, but you can also do the negative square root, right? Because it could be positive or negative. So we got two solutions for x for where the tangent line is flat, and which is square root of 5/3, roughly almost 1.3. So if we were to graph this, well, this is how the graph looks like of this guy. Well, square root of 5/3, negative 1.29 is right around here. This is negative 1.29, and this is positive 1.29. And so you can see that the graph goes flat there and there, which is exactly what we wanted. All right, so those are horizontal tangent lines. Let's go ahead and take a look at some other behavior, some other peculiar functions. This is an interesting function because it's square root. So let's talk about how can we actually take the derivative of a square root function. And then we're going to see how it behaves at x equals 5 because it's going to have some peculiar behavior. All right, so we're going to take the first definition approach. We'll do the first definition first, and then we'll see about doing the next one. So if we plug it in here, we got x plus delta x replaces x here for the first part, and then minus the original for the second part. All right, continue, and then for this part. So for this part, what we're going to do is we are going to we're going to, in fact, that it doesn't actually, there it is. Okay, so it didn't actually show until just now. But what we're going to do is we want to get rid of the square root on the top. So we want to rationalize the numerator. Okay, so remember, to rationalize the numerator, we need to multiply by the conjugate. Okay, so for example, if I wanted to rationalize square root of 3 plus square root of 5, I would multiply that by square root of 3 minus square root of 5, okay? I would actually multiply by that. And if I multiply by that, that gives me 3 minus 5, which is negative 2. And then that gets rid of the radical, okay? So that's essentially what I'm doing here. So I'm rationalizing the numerator, multiplying by the conjugate, the opposite sign in the middle. All right, so if I do that and I distribute this, multiply this together, I get this, right? And that gets rid of the radical in the numerator. Keep in mind that I sacrificed the radical in the numerator for having a radical in the denominator, however, because if I multiply the numerator by something, I have to do it to the denominator as well. So we do unfortunately have a radical in the denominator, but that's okay. You'll see why it works out. So as we continue simplifying, notice that the negative 5s cancel, because if I distribute this turns into a positive. So negative 5 and positive 5 cancel. And then we have x minus x, so that cancels as well. Okay, so these cancel, leaving us with delta x on the top. And you notice that the delta x's here are going to cancel, leaving us with 1 over the denominator. We are almost there. If I plug in 0 into the delta x, I get this. And then notice that these are two identical. They're actually identical, so we can combine them. So if I look at this, the 0 really doesn't matter there. So here, I can combine them into 2 of them. So this is my derivative. And then we're going to see there's going to be some peculiar behavior at x equals 5, right? So if I plug in 5 into here, I get 0 on the bottom, and so I get undefined. So what does this indicate? Well, we remember that if the slope is 0, we have a horizontal line. If the slope is undefined, we have a vertical line. So we actually have a vertical tangent line here. So it's a vertical tangent at x equals 5. And we're going to show you this with the second method, the second definition. So if I were to use this definition here with the C definition, where limit as x approaches c, where c is 5. So let's show you how to do that real quick. So again, plugging in, this is the original. This is the one with where you plug in 5 for x here. But then this is going to go to 0 anyways, right? So it's going to go away, leaving us with that. So this goes to 0. And then we need to, of course, we need to rationalize the numerator. So we're going to multiply by the same thing, top and bottom. And then by multiplying this by itself, this square root goes away. This top part will basically turn into this raised to the second power, right? Which is x minus 5. Technically, it's absolute value of x minus 5, but we're gonna just ignore that and consider the fact that we're just looking at x approaching 5, and we're not really worrying about absolute value or anything like that. But in other words, this actually cancels here. And then we get 1 over square root of x minus 5. But then notice that if I plug in 5 into here, I still get undefined. So it really doesn't matter if I do this absolute value here, because it's going to be undefined anyways. But strictly speaking, we technically would have to write this as absolute value of x minus 5. And write it this way. And then we would have to do it as two one-sided limits. Like, so if I approach 5 from the right side, then I can go ahead and release the absolute value. There's no absolute value on this one, by the way, it's just a parentheses, but on the top there's an absolute value. But if I do it from the left side, this turns into negative, right? But it doesn't really matter, because if I plug in 5 into the bottom, it's going to be undefined. All right, so there is a vertical tangent line at x equals 5, no matter which way you do it. So this is the function square root of x minus 5. It's just a square root function, but shifted by 5 to the right. So then you notice that at here, we have our vertical tangent. So at x equals 5, that's where it goes vertical, and then eventually it starts leveling out, right, as we continue. But in the beginning, it's vertical. All right, so let's look at another example, the absolute value of x minus 2 at x equals 2. So discuss the continuity and the derivative of the function. Okay, so first off, this is how the absolute value of x minus 2 looks like. The absolute value of x looks like this, but then x minus 2 is going to be shifted to the right too. All right, so there's how our function looks like. We can see that it's continuous everywhere. So there's no issues with continuity. However, there is a sharp corner at x equals 2, so we know that it's going to be undefined when we take the derivative there. But we're going to show you how to do that. We're going to take the derivative from the left and the derivative from the right to see what we get. So if I take the left derivative, that is the derivative from the left, right, the limit from the left as x approaches 2 from the left here, we get this, right? So so remember, f of x is absolute value, and then we're plugging in 2 into the function, so this actually just goes to 0, right? So we're left with absolute value of x minus 2. But since we're approaching 2 from the left, remember the definition of absolute value is that this is equal to the original if x minus 2 is greater than 0, and this is equal to the opposite if x minus 2 or greater than or equal to 0, and then this is when it's less than 0. Okay, that's the definition of absolute value. So in terms of piecewise functions, so in other words, if x is less than 2, you can put a negative there. You can put a negative here. So that's why I put a negative right here, okay? Because we are actually less than 2 because we're approaching from the left. So then notice that these cancel, leaving us with negative 1. Now, if I do it from the right side, then there's no issues with the absolute value, because then I can just make it the original, just a regular x minus 2 and not the opposite. But if they cancel, we get 1. All right, so this is showing you that the slope of this is negative 1. The slope of this line is 1, which is exactly what we demonstrated. And so there is no agreement on the derivative at that point, and therefore the derivative does not exist. Okay. So there's a sharp corner, x equals 2. Okay, let's look at example 8. So find the derivative. Again, we're introducing to you a lot of examples just to make sure that you know how to take derivatives and look at a variety of functions, right? So let's discuss the behavior of this particular function. This is a cubic function at x equals 1. This is going to be an interesting one because we have to use the limit definition for this, right? So let's use the first limit definition. So if I do that, I get the original function with x plus delta x minus the original function, right? Now you might be wondering, how in the world are we going to get rid of the cube roots, right? We got rid of the square root by multiplying by the conjugate, right? Multiplying by the cube root is a little bit more complex. Okay, so I want you to recall a few formulas. Recall the difference of cubes formula. The difference of cubes formula, a cubed minus b cubed, is a minus b times a squared plus ab plus b squared. Okay, and how is this going to help us? Well, we want this to turn into something to the cube root of something to the third power minus cube root of something to the third power. That way the cube roots cancel, right, and gives us without the cube root. Okay, and so that's essentially what this is saying. We want this to be something raised to the third power, something raised to the third power, so that the cube roots cancel. Okay, so that's essentially what we're trying to do. We're trying to get rid of that cube root on the numerator. So we have to use this formula to do it. So let's consider that a is the cube root of that and b is the cube root of this, right? The two ones that we have here and here, right? Of course. And so in this formula, a squared is going to be just this part raised to the second power, which is what I got here, okay? And b squared is going to be this raised to the second power, which is what I got here. So we're going to plug this into this formula right here, right? So let's do that. So we're going to multiply by, this is a minus b. Okay, so this is a minus b in this formula. This part right here is a squared plus a times b, and again I'm going to stretch it out so you can see it, a times b plus b squared. So hopefully you can see that that's what that is. So we're using that formula. This is a times b right here. So we're actually using that formula, but whatever we do on the top, we have to do on the bottom, okay? So that's why we do it on the denominator as well. So this formula should give me a cubed minus b cubed, right? According to this. That's exactly what it does. You can FOIL it in order to verify this for yourself, but you don't have to because you know that the formula is going to give it to you. So it's going to be a cubed minus b cubed. That's what we get, a cubed minus b cubed. Now we get that the cube root cancels. So we don't have a cube root anymore on the top. Of course we have it on the bottom, but that's okay. So now notice that no cube roots on the top. So x's cancel, the negative ones cancel, leaving us with delta x on the top. Notice that delta x cancels as well with the delta x on the bottom because we only have one on top, one on bottom. That cancels out there. All right, so if I look at this, the numerator turns into 1 because the delta x divided by itself to get 1. And we just have the denominator, and what we did is we replaced delta x with 0, so we made a substitution there, and that's it. All right, so we don't need the limit anymore, the limit symbol, because we plugged in 0 into delta x. But notice that these things are all the same thing, right? So this should actually be this should actually not have a squared there, so I apologize for that. That should just be to the first power, not to the second power. But these things are all equivalent, so we can combine them. So I'm just going to show you what we had. That's this part right here. But like I said earlier, these are equivalent, so we can just combine them and make 3 of them. All right. All right. There is our derivative. So that was a lot. So we took the derivative of that function. Very simple looking function. Doesn't look that complex, but then there's a lot to it, right, to get the derivative. Well, we got the derivative, and then we can plug in x equals 1. But notice that if we do that, there's going to be 0 on the bottom, so it's undefined. So again, we have a vertical tangent at x equals 1. So something interesting about that. So let's take a look at the graph. So if I look at the graph, notice how the behavior changes dramatically here. It changes dramatically at this point. And so here you got the tangent line that goes like this, like this. Then it goes like this, and then it changes dramatically. It goes vertical, and then it goes like this, right? So there's a dramatic change, so that at this point you get a vertical line at x equals 1. Okay, and that's why we got that. We can see that from our derivative that we did. Okay, so here's the thing. So let's apply. So now we know how to take the derivative. We've seen a few examples of that. Now let's go ahead and take a look at the idea of continuity and differentiability. So it turns out that if f is differentiable at a particular value, then it must be continuous at that value. If you think about it, that doesn't make sense. However, if it's continuous at that value, it doesn't necessarily mean that it's differentiable. In other words, this only works one way. It's not guaranteed to work the other way, okay? Because remember that when we had a sharp curve like this, it was continuous everywhere, but you couldn't take the derivative there, right? So it doesn't work both ways. It only works, it's only guaranteed to work one way. In other words, if it's differentiable, then it must be continuous. Okay, so looking at this example, this is the cube root function that went like this, right? It wasn't differentiable here because, I mean, I say that it wasn't differentiable at x equals 1, and I say that because you can't take the derivative of that because it's infinite, right? So that's what I mean by it not being differentiable. I mean, it's infinite, right? So it's a vertical line. So basically the derivative is infinite there. You don't get a specific value. That's what I'm trying to say. Even though it is continuous, now it's differentiable at 0, but it's also continuous at x equals 0. So for example, the derivative of this we said was 1/3 times the cube root of x minus 1 squared. Well, if I plug in 0 into this, I get 1/3 cube root of 0 minus 1 squared. Notice that there are no problems whatsoever in taking the derivative at 0. There's no problems in plugging in 0 into this. So it's differentiable at 0. And it's also continuous at 0. We can see that the function is continuous everywhere, right, from that graph. So in other words, if it's differentiable at a point, then it's continuous at that point. We're going to prove this. So this should say x equals c. Should say x equals c. Okay, so if it's differentiable at x equals c, then that means the derivative below has to exist, right? So we're going to prove this. This is sort of like a proof. Okay, so if it's differentiable at c, then that means we can take the derivative using that definition. And then we're going to show that when f of x equals f of c, that can only be true when x approaches c. So as x approaches c, this becomes the one and the same thing. And we want to show that this is true in order to prove that it's continuous. So we know that it's differentiable. We want to prove that it's continuous, okay? So we're going to try to use this to prove it. Okay, well, if f of x equals f of c, then that means f of x minus f of c must be 0, right? So then what we're going to do is take the limit as x approaches c. That's what we wanted to do here to prove that it's continuous. But then we know that this can be rewritten as this times this. So for example, I could rewrite f of x minus f of c as this over 2. But then if I divide this by 2, I have to multiply it by 2. That's exactly what I'm doing here. And notice that those cancel, right? And leaving us with the original. So we are rewriting it in a slightly different form. So we haven't changed anything. However, we're going to say that is we're going to distribute this limit. And as we distribute it, we can see that if I plug in c into here, we get c minus c, which is 0. But if I plug it in here, this is just a definition of the derivative. Remember? That's the definition of the derivative right here. So this actually gives you 0 times the derivative at c is 0. And so what it's saying is that, yes, we do get 0 when we plug in this limit. So if we get 0, that means that f of x must be equal to f of c, and it must be continuous at x equals c. Okay? But notice that we're at a roadblock if this is not if this does not exist. Because if this does not exist, we cannot say it's continuous, right? But we assumed that it exists here, okay? And therefore, if it's differentiable, it must be continuous. All right. So that's a quick proof there. But we're going to go over one last thing here, how to find the equation of the tangent line. So we've gone over how to find the slope of the tangent line. The slope of the tangent line is the derivative of this line, right? So we know how to do that, but how do we find the equation? Well, remember from Algebra 1, you know, this is the equation of a line, right? The equation of a line is, this is the point slope form of the line. The point slope of the form of the line is y minus y0 equals m times x minus x0, right? That's the equation of any line if you're given 2 points and a slope. Well, that's what we're doing here. M here is m tangent, right? So it's the slope of the tangent line. But we said that the slope of the tangent line is the derivative. So we're going to replace the m tan with the derivative symbol. We're saying f prime, okay? F prime at x0 is m tan. So this is m tan, okay, in terms of the derivative. And we know how to do the derivative, so then we can do this. So let's look at an example. So remember this crazy looking function? This is a function that kind of look like this, right? So we're going to take the derivative of that. And then we're going to find the equation of that tangent line at x equals 1. Okay, so first off, we know that, you know, the equation is y minus y0 equals derivative times x minus x0. All right, so remember that this is x0, this is y0. x0 is 1 and y0 is square root of 3. How did we get that? We just plugged in 1 into that function, right? And this is what we got. So now we got our y0 and our x0. So now we need to get the derivative. So that's what we're going to do next, okay? So we're going to do the f prime at x equals 1 using the second definition of the derivative. This is going to take some work here. So we got f of x is this guy. This is the original. And then this is the original with x when you plug in 1. So this is what we get. We get this turns into 3. So this is going to be square root of 3. All right, so we got that, and then we're going to need to rationalize the numerator. So we're going to need to multiply by the same thing, but opposite signs in the middle, okay? All right, so then upon doing that, we get something that looks, where we're about to multiply now. So let's go ahead and multiply that. So when we multiply that, we get this raised to, this times this is just this to the second power. And this times this is just this to, it's going to be 3 because square root of 3 squared is 3. So this is what we get when we FOIL. All right, so now next we're going to distribute the x squared to get the top there. And we're going to pull out a -1 from this. Pull out a -1 from there. If I pull out a -1, I get this, okay? I guess, and I rearrange a few terms. This is what I got on the top. The reason why I do that is because we want to factor. So we're going to factor the top. So we need the factors of 3 that add up to -4. Well, the only way to do that is if you have -3 and -1. That's why I have -3 and -1. Then we factor it into those two terms. Remember, this is x to the 4th, so when I factor it, it's going to be x to the 2nd power. All right, so that's how I factor it. And then we can factor this further into the difference of squares, right? So a squared minus b squared equals a plus b times a minus b. This is how you factor x squared minus 1 into those two, x plus 1, x minus 1. Again, there's a lot of things involved that goes along with this problem. And then notice that when we do this, that the x minus 1's cancel. And then we can start plugging in 1 here, 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 and here. So we start doing that in the next step. Start doing that right over here. We plug in 1 into that expression. Sorry, I'm going to zoom out again. All right, so then when we do that, we get 2 over square root of 3, but then if we rationalize that, we get 2 square root of 3 over 3. Shoo, there's our derivative. So now let's summarize it. So far, this is what we have. We have y0, we have x0, we have derivative at x0. So we can plug it into the equation of the tangent line, which is that. plug in your y0, f prime of 1, and x0. Okay? And there's our equation. I'm going to distribute this here and here to get this. And then I'm going to add the square root of 3 to the other side. That way I can solve for y. And I get this. And then we can combine these into one fraction to get square root of 3 over 3. Again, if you wanted to see that, remember that square root of 3 is over an invisible 1. We can multiply by 3 in order to get a common denominator. But if I multiply that by 3, I have to multiply this by 3. And negative 2 plus 3 square root of 3 is negative 1 square root of 3. That's how I get this. Okay. This is the equation of my tangent line. I know it looks simple compared to like all the work that we did that went into it, but there's our equation nonetheless. All right, guys, that is the end of the lesson. I hope you learned a lot from this video with the definition of the derivative. We're going to look at some shortcuts for doing derivatives after this lesson. And so it'll make this process a lot more streamlined, simple. But I hope you learned a lot from this video. And as usual, I'll see you in the next one.